a very fundamental concept of math, and this would be the concept of exponents. Essentially, what all exponents do is that we take certain bases, or say certain numbers, and we're taking something and we're multiplying it by itself a certain amount of times. So say we have our base by a power. Now, another way also represented computationally would be, say, which this asterisk is just, it's not, in this context, not an and. It would be just, say, like, if you're typing it out, it would just be like that. Say, we have 2, would be our base, and we would have our power, or say, otherwise we want to represent it like this. In this case, 2 times 2, because we're taking the base and we're going to do it 2 times, which would give us 4. Now, that's essentially the concept. It's a very simple premise. In math, we want to do little shortcuts. We want to have shorthand ways of representing things. You don't really want to be writing out 2 times 2 times 2 times 2 times 2, because it would be like, it would be ridiculously long, and at a certain point you're just going to lose count. And if anything, the way that notation wise it just makes sense like that. To also put it in, I guess, a more appropriate variable form, say our base would be x, our power would be a. Now, a can be really anything, any imaginary value. But, a can say, really be kind of anything. Right? X times x times x times x. It can go to infinity, really. But, okay, so there's certain rules and properties to exponentiation, just generally because it just makes the most sense in that manner. Let me just kind of shift down here. So, say we have a base of x, and this would be our product rule, or way that we're going to essentially multiply an exponent by an exponent. Which product is just a fancy way of saying, I keep clicking that thing. Just a fancy way of saying multiply. That's all product is. So we have, say, a common base of x times x of b. Now, bases have to be the same. You can't have, say, different values. If anything, it just messes up the whole premise of it, and it doesn't make any sense. And really, what signifies that, a multiplication process simply is just how many times we're adding something. Just as division, which we're going to cover after, all you really do when you see you multiply an exponent by an exponent, you just add. Again, the process of multiplication, and essence of the way the operator behaves, is just how many times we're adding something, and which, is a very convenient shorthand for that. Now we want to get into something called the quotient rule. Now, vice versa. Say we have a common base of x by x by b. Now, again, operator of division, that all you're really doing is how many times are we subtracting something from itself, right? So, in that case, we would be subtracting the powers. Which, say we want to take a power to a power. So, I'll call it power rule. In essence, say we have in brackets x to the a. Now again, x is our base, this is our power, but let's say we want to raise a power to a power. Let's say n would represent another power, which in this instance, you're essentially going to take x, you're going to take a, you're going to multiply it. So, another fundamental rule, in which, this is more like, say, a rudimentary identity rule. Which, say, in an instance, if we have x be raised to a power that's, say, to 0. So there's nothing here. Now, just say, like, when you do a factorial of, say, a value, this would automatically immediately be represented as a 1. And that's because you cannot, you can only evaluate a base by itself, like, if, say, the nullification process. You're only doing that operation once, if anything, so that's why it would be represented as 1. Now, what if we have, say, a property, and this is another property, and we'll call it the reciprocal rule, which I probably misspelled that, but again, I'm doing some math stuff, so it is what it is. Reciprocal rule essentially states if we don't have a positive power, we can have negative powers as well. So base of x by negative of a. Again, my a's look like 9s and my 9s look like a's, so I'm going to try not to confuse people too much, but no promises. Now, essentially what we're doing right here is, because of just the way that you have to shift back and forth, like just imagine a number line in your head for a minute. Positive goes to the right, negative goes to the left. Now, if you're diminishing and decreasing in value, again, we're going to essentially take this power, and you're just going to assume it's a fraction immediately. Because, again, you're decreasing in quantity or decreasing in value, or say we're multiplying a certain value, but you're shrinking it almost, I guess. That's reciprocation in essence. You can also represent this vice versa, meaning that you have, say, 1 to the x of a. You can also do this, represent it either way. I find that if anything, with powers, and that especially when we get into derivatives and all that fun stuff. Um, it's just a lot better to represent things in that way. Now, let's kind of just put some of these concepts into practice, because again, some good visual examples would help. Which let's do a simple product rule example. So I'm going to signify this as example 1. We'll say we have a common base of y. We want to take 2 power and by 7. Again, the bases have to be the same. If they're not the same, then it won't work. So again, all you do is just add. And that's pretty much it. There's no really magic guesswork in which, we can verify this anyway. If you plug any value in, right here, you raise it to 9, it should give you that, as if you say split it up. Say y times y twice, plus y times y 7 times, say. And you want to combine them. If you need to verify, it is what it is. It's always good to verify, especially if it's new. But I'm not going to do that, because that's just kind of what it is. So that would be our product rule in action. Now, let's find a good example of a quotient rule. Say we have, and again, sometimes we're not going to encounter just single bases. We're going to have a scalar in front of the base, which all a scalar is how many times we're raising it. I'll cover that in a separate topic when expanding. But say we have a value 2 to the x of 6 over x. Now, x by itself, we don't write it like 1 typically. It's just assumed it's 1 on its own. So what we're essentially going to do right here is we're going to take 2 x to the 6, and we're going to subtract it by x, which in this case, also can think of it as 2x6 minus 1, which would give us x, or 2x to the power of 5. So that's our quotient rule in action. Now, say we have our power rule. Now we can, I don't know, say we have 2 pi to, say, power of 3. Now, again, this power, again, you always think of it as 1 if there's no power wrote right here. Now, we're going to associate this with each member. So the base by the scalar. We'll say which 2 to the power of 3 would be 8. So 2 times 2 times 2. And say pi to the power of 3. We'll just leave that alone. Because again, pi goes on forever, and that's the constant, so I'm not going to write out whatever floating point value that may represent. But that's what it is. Another example I could probably demonstrate for the power rule, or power to a power rule, would be, say, I don't know, say a or no. What would be better here? Because we want to kind of now combine a couple of different rules. Say, quotient rule to a power rule. So say we have value like that, which we'll have over 2 to 4. I apologize if my dog's barking. I can't control her. Now, in this case, what we're going to want to do first before we even perform this action inside is we want to do our power to power. So again, 2 times 4. And then this right here, it will go right there. Which in this case would be x to the 8. And then 2 times 2 times 2 times 2 would be 16. Just like that. Just like that. Now, say we have, I don't know, because a good way to signify the identity rule would be, say, let's have value, I don't know, maybe 8 y to 0. Now we're going to kind of just combine the identity rule with the product rule. Now again, or not product rule, power rule. Take each member, you associate it like this. Which again, logically, how it should correspond. 8 to raised by itself, well, you're only doing it once. Y by itself, again, whatever dummy variable you want to, in which this dummy variable can be assigned to whatever, it's still going to be 1. 1 times 1 is 1. That's it. Say we have a reciprocal now we want to deal with. We'll just say alpha to power 5. So say negative alpha to reciprocal of 5. Essentially all it is just this realistically. And that's a negative in front. I apologize. It looks a little bit disheveled. Now, what we also want to show is let's do a little bit of a fancier example here, just to kind of clarify certain concepts. Let's say we have I don't know, 3m by power 4, and we want to say have it raised to this point. Now again, we got to do this procedurally. I always tend to like to do my powers first, and it just makes the most sense. So, say we take each member, we associate it to the power. So negative 2 times negative 2, that would give us positive 4. Which, what do you call it? Negative 2 times this would be negative 8. Because again, we're taking that, multiplying it, each little value. Now, what we want to do is then do this. It would be 9 right down there, and since it's going to be living downstairs now, 3 and negative 2, that would be our denominator. Our numerator would pretty much live right here. So it would live upstairs, and then n to power of 8. And, pretty much like that. Oops. My apologies. Let's get this. Okay. Yeah, and I'm still kind of getting used to the way that Microsoft Whiteboard works. Another example we can do here. Let's say N R T, which, if my chemistry time isn't wrong, this would be a gas problem that we're dealing with. Because again, our powers can be as high as you want to kind of get them. Now, what we're going to do here is we're essentially going to do our power rule first. N32, R32, negative 2 times 32 would be T64. This would remain the same, so R negative 2, T32. Now what we want to do here, we want to move that to the basement. This is the way it goes. So N32. R32. To the basement. So R2 T32 T64, which we're going to just be adding those because it's a common base. So that would be 96. So N32, R32, R negative 2, and then T96. Now, funny thing is that notice that I kept this a negative on the bottom, and for a very good reason, because actually reciprocal rule works vice versa, so we can put this on the top actually now. 32 R32 R2 T96, which in this case we just add these two together. 32 plus 2, that's 34. So N32 R34 over T96. And we also could represent this as n32, r34, and t to the reciprocal of 96. Just like that. And there's a lot of different ways that, if anything, you can interchange and, kind of play with these rules. That was just a little bit of a bigger problem, just kind of combining everything we learned and we kind of delved into. Say just for fun, let's do another real problem here. Which this is a pretty good one, I think. If I'm not mistaken, this would be a wave problem, quantum mechanics. So, say we have g to the m over 2 pi f c by, that would be c, bracket 2 pi f m squared, which in this case, how we're going to begin is we're just do our power by power, gm 2 pi f c power to a power, so that would be 4 2 f2 m2, and then what we want to do right here is we want to just take each of these members, because now all we're doing is, again, power by power, or not power, product rule. We're just multiplying it. So take our scalar factor, GM, we're going to leave alone. So that would be 8. This would be pi 1, pi 2, so that would be 3. Same with F. Same with now M. M doesn't go anywhere. 2. And then we have our C by itself as well. Now, what we're going to want to do is we're going to just want to roll this down a little further. Now we have a common term at the top. That essentially G is by itself. This again, we're going to be subtracting M from M. So pi 3 F3 1 minus 2. Now we're going to have just only reciprocal of -1 right here, which M would be the adequate representation by C. Which, that's a pretty, it's this wave function problem, it's a pretty common application for such things, right? But yeah, what we can do also for our final example is, again, I gotta end the video at some point. This would be an orbital problem. So say example 10. I keep clicking that on accident. I'm gonna get used to this pen at some point. Okay, so we have G M to the M M R -1 R -2. Now we don't have anything outside here, So it's not raised to a power. So it's automatically assumed to be 1. So we don't gotta worry about that. This is just, if anything, the parentheses it's just to make the problem look a little nicer, if anything. But okay, so we leave this alone. We don't do anything here yet, but power to a power. So we have m negative 1, r negative 1. We leave this alone for now. But this is where things are kind of get a little bit cool here. Is we want to kick this to the basement. M1 R1 R2, which again we just add these G M to M. No, that's not R1 plus 2, which would be 3. And yeah, pretty much that's our kind of illustration of exponents and different way we can interchange them, move them around, in which the rules kind of cascade on each other. Hopefully this kind of gives some insight and help. Which, this is my first one of these, and hopefully I can make more. Anyway, thank you very much for watching. Support the channel, and God bless.